Right, so we're in BC calculus. We are talking about polar functions today. Today's date is Monday, February 3rd, 2/3, 2020. Things that are in the news, the coronavirus. Our objective today, I didn't hand out the cards because we don't use cards in here. Fiona, what is our objective? Yeah, notice that I don't say graph functions by hand because graphing polar functions by hand is tedious. They don't expect you to do it on the test. I'm not going to expect you to do it on the test, but you should know what cool things happened on the graphing calculator. But first, before we begin, let's start with some vocab. So first of all, if we're in polar form, we have a pole. Where is that pole? And it's a little bit review, but some of the stuff is brand new, right? So this is the pole. It's right there. It's what everything revolves around. So I'm going to call this thing the pole. This is the definition of what makes me have a polar form. For all of math in high school, up to even BC calculus, your pole is always going to be at the origin 0, 0, so don't worry about it. When you study math in college, if you decide to go on that route, your pole can shift around and help you out. But yeah, 0, 0. We always have two different inputs. Very similar to your normal Cartesian, you have an x and a y. This one, you have a radius and you have a theta. So this C right here, or any polar forms, we'll say we have something, comma, something. And this something is going to be the radius, comma, your theta. Or does it go the other way around? Usually, I think it actually goes theta radius. It doesn't matter. You have two inputs. Theta is your angle, your argument. We'll say this is your angle or your argument. I don't usually use the word argument very much. That's a little bit formal. Argument. I'll put that in quotes because I don't use it as much. And then R is, you want to think about this as your length. This is your length. Your length as if I was attaching this point to the pole. And make sure, James, you're still copying down the notes. Did you write down the word length? All right, and then another word for length is the modulus. Those are synonyms of one another. All right, so I want you guys to help me out right now. What are the coordinates? Well, it's not the exact coordinates, but like what is the theta? What is the argument of this C? And notice here that this grid is broken into 1, 2, 3, 4, 5. So into 6 different regions. I have region 1, 2, 3, 4, 5, 6 regions, which means really what I have here is pi over 12. Pi over, each of these is pi over 12. So another pi over 12 and pi over 12 is pi over 6. So 3 pi's over 3 pi's over 12 is pi over 4. Each of them is pi over 12. I'm just adding on another pi over 12. So this is going to be pi over 3. And then this is finally going to be, I guess, 5 pi over 12. We don't really use these two, so you can kind of scribble them out, that one and that one. We don't really use pi over 12 and 5 pi over 12, but we do use all these other ones. And then we finally have pi over 2. And I could go all the way around this unit, or it's not even a unit circle, it's a polar graph. But I'm not going to because I think you guys can figure it out. Like the main 3 lines, if I had to highlight them, you should highlight yours as well. So it's the inner 3. So this one, and this one. The inner 3 are the ones that you care about the most because those are the ones that have these special right triangles that we know and love. Everyone nod your head. Do you love special right triangles? Nod your head up and down, Teflon. You're shaking it the wrong way. It's a common mistake. Don't worry, I won't tell anyone. So we know what's going on here. So what is the argument of C? I've already listed it. Can someone give me a quiet raised hand and tell me what the argument or the angle is for C? What line is it on? Quiet raised hand. Who's got this? Just read it off. I listed it right there. Yeah, Andrea. There it is, pi over 3. And what is the length of that line to get out to C? Yes, Teflon. Careful. It goes on this line right here, and this line is connected to 3. Yes, thank you. What about for B? B is going to be a little bit difficult. Each of these usually means 1/12. So I know in order to get all the way around, you should remember what that measurement is. And then I need to add on another 1/12, another pi over 12 to get to that coordinate. What is that coordinate? I'll help us out because we're still thinking. I got to pi here. Pi is 180 degrees. And then I add on another pi over 12. So how many pi's over 12 do I have? I'll tell you the hint. It's some denominator. I could just count up the lines, right? Each of these lines represents 1/12. So I have 1/12, 2/12, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 pi over 12. And then I have another 12. So how many 12s have I counted so far with a quiet raised hand? Eva. It was off the desk, but I'll ignore you. Teflon again? It is indeed 13. Gio, do you agree? Yes, it is indeed 13 pi over 12. And then we do the next coordinate. What is the modulus, or what is the length of coordinate B, Chris? How long is this line right here? 4, exactly. And kind of an important note, you should always have a positive number here because it's always a length. Length is always a positive number. Cool. So we have all that copied down. I am moving on now to our next segment. All right, so here are some key facts. They're not going to help you too much on the homework, but they will help you in the future. So I'm kind of preloading you guys for later. So whenever the radius is equal to 0, the point is on the, what's that word that you just learned? When it is pole, but I should be expecting quiet raised hands from you guys. Thank you. It is the pole. So I say most polar functions, but I should really say all of the polar functions that you'll be seeing should have multiple places where something I just talked about, where the radius is 0. So know this, you will have multiple places where the radius is equal to 0. And if I'm talking about, if I restrict it to some specific domain for your theta, then it might only be 1. It might only be 2. But generally speaking, your domain, if I don't restrict you, you'll have an infinite number of places where r is equal to 0, unless I'm giving you some weird, really hard function that's not really in AP calculus land. And another cool thing about polar functions is when I'm halfway in between the zeros, so let's say I have a 0 at, I don't know, pi over 2, and then I have another 0 at pi. Then halfway in between pi over 2 and pi, so let's say in between here and here, halfway in between here at 3 pi over 4, I would have something interesting happening. Halfway in between the zeros, the distance, or your r, will be at a max. Your maximum value always happens, well, yes, always happens between your zeros halfway. All right, and finally, let's move on to some example problems that you'll be seeing on the homework tonight. And this is going to heavily review your trig. So hopefully we know our trig. I guess I can add on some review area. So I want to find any angle measurements between 0 and 2 pi that make r equal to 0 for this cosine squared of theta. So remember that this is the same thing, I can write underneath, this is the same thing as 3 cosine of theta to the power of 2. That 2 on the inside of the outside, we usually leave it on the inside like that. But really, you need to be thinking of cosine of what squared, and then multiply that by 3. How do I make that thing equal to 0? There are a few different ways to approach this problem. The main thing to see is, like, where's cosine 0? So cosine. Cosine, is that the x or the y coordinate? X coordinate. So let's come out here and make a unit circle to help us really quickly. Make our unit circle. Ooh, I can draw, my tablet is slightly crooked. That's my explanation for my crooked line. So if I'm on my unit circle, let's go ahead and I can hold shift to make this a nice circle. If I'm on my unit circle and I'm talking about the x coordinate, where on this unit circle has an x coordinate that is 0? Do you guys see it? Point to them. Where is the x coordinate that is 0? Point to it. There's at least one. I'll tell you there's two, actually. X coordinate that is 0. Remember, this is your x-axis, so in order to have an x-axis that is 0, you're somewhere on this axis, and therefore the point happens right here and right here. Those are the 2 points that make cosine 0. And these are the answers. I just need to write them down. So this is what? With a quiet raised hand. What is this angle measurement? At the very top, Gio? Pi over 2. Good. And then what about the very bottom one? This is pi something with pi. Sorry, Gio. I want to give it to someone else. Eva? 3 pi over 2. Good. Make sure that you have these memorized. So those are the answers. So whenever I do pi over 2 or 3 pi over 2, and those are both between 0 and 2 pi, that is what's going to make r equal to 0. So our answers are pi over 2 and 3 pi over 2. Why does that happen? Well, when I plug in pi over 2, the x-coordinate of pi over 2 is 0, so cosine of pi over 2 is 0. 0 squared is 0. 0 times 3 is 0. Radius is equal to 0. And that's about the level of difficulty I'm going to be doing on the homework. The hardest type of problem I can give you is like example number 2, where you're just looking to make things 0. So this one is slightly harder. Sometimes I like to multiply things together too. How do I make this thing equal to 0? I'll show you a different way of solving this one. If I need to make r equal to 0, just say, okay, r is equal to 0. 0 is equal to 5 times the quantity of sine of theta minus 1. Okay, let's divide both sides by 5. Therefore, I need to have 0 is equal to sine of theta minus 1. Okay, well, now I can add 1 to both sides. I maybe should be alternating my colors every other line to be able to distinguish them better. If I add 1 to both sides, now I say 1 is equal to sine of theta. And that's kind of an easier problem to answer because sine is asking for, oh, I'm going too fast, I'll let you copy this down.
Wait, did it just like slide out?
Not figured out. I didn't know anything going into it, aside from the fact that I had to get the nut out. You should be copying out these notes, Chris. This is a much easier problem to answer. So where do I have a y-coordinate that is equal to 1? I divided both sides by 5. 0 divided by 5 is 0. Yeah. Oh, sorry. I didn't mean to be so aggressive in how I said that. I apologize. All right. So again, I'm thinking of the unit circle. So let me come back and copy paste this circle. So if I have that unit circle, where do I have a y-coordinate that is 1? I can draw a slightly superior circle and axis to this. Where do I have a y-coordinate that is equal to 1? Point to it. Where is it? A y-coordinate that is 1. A y-coordinate that is 1. Not an x-coordinate, but a y-coordinate that is 1. A y-coordinate of 1 happens only at one point, and it's right here. Not negative 1, only 1. And that's the answer. Where do I, because again, I convert this to where is y equal to 1? And the answer is pi over 2. So theta, therefore, is equal to pi over 2.
Cool.
So again, I could have used the same perspective coming back here. If I divide both sides by 3, if I take the square root, then I'm looking for where is cosine is equal to 0, aka where is the x-coordinate equal to 0? Where is x equal to 0? And this one is where is y is equal to 0, or y is equal to 1. That's all I have for you guys. It's very, very similar for the homework. There is a graphing portion of this. I'll show you that right now to see what these look like.
Come on, dude.
They're pretty cool.
It looks way too difficult.
No, you guys got this. I'll do the video with you guys. I'll start doing the homework with you guys. But
Can I go to a restroom?
after I finish showing you this.
Sure.
So to do polar form, let me make this in projector mode and maybe a slightly smaller screen so that it's on the entire screen here. So there's a function in the side here where if you make sure you're in radians, it is in radians by default. But check this out. I have this grid. I can change the grid so that it's in polar form.
Whoa.
So you can see all of your pi over 6. All of those are nicely labeled for us. And what else would be nice to see here? Let's actually start graphing things. So I don't remember exactly how to do this. Do you say like R is equal to sine of theta. Does that work? It does. Cool. R is equal to sine theta. You can see, oh, it's just a circle. Or I can do sine of theta times cosine of theta. Oh, look at that guy. Or I can do, what happens if I do 2 cosine of theta? It gets bigger. What if I do plus 1? Whoa! What happens if I square that last one? Squared it? Okay, it only keeps it positive. What happens if I subtract, I don't know, 2 sine of theta? And this is where you start getting these really cool functions that I would like to turn into a t-shirt or a logo for our shirts. So you guys need to eventually play around with this after you finish now your last 2 homework assignments.
We got to do that with this?
Yes. Yeah, and again, being able to graph this thing is difficult, so that's why we have the graphing calculator, both on Desmos and with our TI-83s and TI-89s. All right, that is the end of the lesson.